Hello, and welcome to my third video about trigonometry and its history. In the first two videos, trigonometry was confined to plane geometry, really, but now it's going to advance beyond that. So in the 17th century, there was an explosion in the development of mathematics and physics, science generally, in fact, fed in large part by the development of calculus. Mathematics and science fed off each other, and trigonometry played its part in that. So the first video was about right-angled triangles. That pretty much is the content of the first video mathematically. The second video, we talked about different definition of sine and cos, which extends it for obtuse angles. All sorts of mathematics and history we talked about, and in particular, the fact that the graph of sine and cos look like waves. But now we're heading off towards calculus. But to start with, let's look at this little theorem that I'm sure you know. We might say here that the angle at the circumference is half the angle at the centre. But in some countries, they draw that picture and say that the angle on the circumference is half of the arc on which it stands. That's rather interesting, isn't it? So that means they're measuring arcs in degrees rather than as lengths. We used to do that in English too, but we don't so much nowadays. A little while ago, I found a mathematical dictionary, which was, I think, early 19th century. And I looked up degree, and it defined it as, its primary definition was a 360th of the circumference of a circle. So there it was thinking of arcs as measured in degrees rather than in miles or feet or whatever they'd have been using in those days. So that's interesting. It raises the question of what are we using to measure arcs and angles? What units do we use? And it's time to introduce a new unit beyond degrees, which is the radian, which at first sight seems a rather odd unit. So it's a pith of 180 degrees, or if you like, a 2π of the whole way round, of the whole circle. And it's approximately 57 degrees. Which is very strange until you look at this arc, because what it's saying here is that if this is 1 radian, and this is a circle of radius 1, then this arc is 1 because it's a 2π of the whole way round. And so that's the definition of a radian we normally have. It's that angle for which the arc is equal to the arc length is equal to the radius. So what's the history of this radian business? Well, it possibly goes back to this guy. I think we've not met him before, Al-Kashi, writing at the beginning of the 15th century. And amongst other things, he wrote this book. That's interesting. So you will recall that the first people to do trigonometry, Hipparchus and Ptolemy, used the chord function rather than the sine function, whereas Brahmagupta in India used the sine function. Well, the people in Persia at that time were aware of both traditions, and so he wrote a book about it. He had many accomplishments, including, this is rather interesting, computing 2π to 9 sexagesimal places. So it's interesting, that's 16 decimal places, that's quite a lot. But it's interesting he was still using sexagesimal as the Babylonians had been doing 3,000 years earlier. And apparently he used what are translated as diameter parts to measure angles, which is asserted to be a 60th of a radian. I have to say, diameter part sounds to me more like a 60th of 2 radians. That is to say, the arc length equals to twice the radius, the diameter. But I don't know the truth of that matter. So the radians were implicitly used in the Kerala school in the 16th century in India, because some of the formula clearly imply that that's what's being done, but they don't actually define the radian. So the honour of defining the radian is usually granted to this Richard Coates guy. And this is, I think, the first time we've met in these videos a concept first used in modern Europe. So trigonometry arose in ancient Europe, in Greece, and the Greek-speaking world, and then spread to India and back through the Middle East and North Africa and back into modern Europe. Right. So it's adopted by other people, including Euler, who saw the light. And it eventually became the SI unit of angle. It turns out that radians is the proper unit for doing higher level maths. And so if you're building bridges or cutting pizzas up, you'll continue to use degrees. But for higher maths, you're going to be using radians forever now, really. So you better get used to it. So in this video, I will present a series of increasingly convincing reasons why radians are the proper unit to use. And this is the first one. This is not terribly convincing, but it's quite pretty. So let's look at a circle and consider the length of this arc. The circle is the radius r, and the angle there is theta. So the arc length, well, it's the whole way round times theta over 360, because clearly the arc length is proportional to the angle, and the constant of proportionality is theta over 360 if we're working in degrees. And that simplifies a bit to r theta times pi over 180. Well, that's okay. Do it in radians, though, and, well, we've sort of done this, really, haven't we? Because the arc length is 2 pi r times theta over 2 pi. Again, it's the same constant of proportionality, but now we're working in radians, and that simplifies to r theta, which is a good deal prettier. Then we can do the sector, the area of the sector. It's the same argument, because the area of the whole circle is pi r squared, so, and it's going to be proportional to theta. So, and the constant of proportionality turns out to be, well, if you simplify it, it's pi over 360. Doing it in radians again, it's pi r squared times theta over 2 pi, and that turns out to be a half r squared theta. So these two formulae are much prettier than those ones, but I don't expect you to be convinced by that, that radians are the right unit to use, although it's a sort of beginning. Here's another reason. So in the books, you'll see this. So when theta is small, sine theta is approximately theta. Well, that's a pretty daft thing to say, really, isn't it? Because of course sine theta is approximately equal to theta if theta is small, because they're both approximately 0. So what's actually meant is something much more precise than that. And it's this. So this is a smaller symbol, but it's more precise. This has a precise mathematical meaning. It's pronounced twiddles rather cutely. At least it is in mathematics. Of course, it's a tilde, really, but there we go. And it means this. It means that sine theta over theta tends to 1 as theta tends to 0. In other words, as theta tends towards 0, sine theta not only tends to 0, but actually it does so at the same rate as theta, if you like. So theta over sine theta get increasingly close to 1 as they both approach 0. So that's a much more precise statement, and that's what we should be using. So let's prove that. So here's a circle, the radius 1, and we've got 3 triangles. We've got this littler triangle and this bigger triangle, and in between we have the sector with this blue arc. Okay, so let's look at the areas of those things. So the area of the smaller triangle is a half sine theta, half base is 1, height is sine theta. The area of the sector, of course, is a half alpha. We've just seen that, the radius being 1, and the bigger triangle is a half 1 times tan theta. So we divide that by sine theta, which is positive, so we get this. And actually, it's better to look that the other way up. All those terms are positive, so we can do that. So what does this tell us? Well, it tells us that sine theta over alpha is between cos alpha and 1. And cos alpha, we know easily, tends to 1. So sine alpha over alpha is squeezed between cos theta and 1. So it definitely tends to 1. Let's watch what happens as alpha gets small. So cos alpha, that's this length, is definitely tending to 1. And so sine alpha over alpha must be tending to 1 as well. Well, that deals with positive alpha, but actually it works in negative alpha as well. I mean, if you replace alpha by minus alpha, this equation is just the same. And here it is illustrated. So the red thing is the graph of y equals sine over alpha. The green thing is the graph of cos alpha. And the black one, of course, is the graph of y equals 1. Okay, so that's that one established. But let's look at the properties of this twiddly thing, which we'll need later. So if A twiddles B and B twiddles C, then A twiddles C. So it's transitive. We should also need this relationship later. So if A twiddles B and C twiddles D, then AC twiddles BD. Well, that's sort of obvious, isn't it? Because A over B tends to 1 and C over D tends to 1, then AC over BD tends to 1. Okay, so we'll need that later. Oh, this is just an illustration of that relationship we've just seen. So here is some small values of theta going down to 10 to the minus 5, and here is the value sine theta over theta, and you see it's definitely tending to 1. And here's the graph. I mean, what this tending to 1 really means that this line y equals theta is tangent to the curve. And here it is tending to 1. There's something else going on here, isn't there? I mean, this is not a random number, is it? So there's something significant going on here, which we'll meet later. So the other small angle thing that you see is this. This is even dafter than the other one because, well, of course, cos theta is approximately equal to 1 minus theta squared over 2 because when theta's small, because it's approximately 1. So that's not what really meant. Even that's no improvement really, because of course cos theta twiddles this lot because it twiddles 1 and this twiddles 1. So it's obviously cos theta over that lot tends to 1. What's really meant is this, which you see as a slightly subtler statement. So it gets hold of how far cos theta is away from 1, and the difference twiddles theta squared over 2. That's a much more precise statement. And actually it's easy to prove given what we've already done. So 1 minus cos theta by the double angle theorem is that. Now, just to go a little bit cautiously, so sine of theta over 2 twiddles theta over 2, and by the multiplicative property of twiddles, the square of this twiddles theta squared over 4, so double it twiddles theta squared over 2. Right, so we shall be using those later. Here we go. So let's look at the derivative of sine. We'll work from first principles. Sine of if you like changing y over changing x, if you like, or if you prefer the algebraic version, sine of theta plus a little bit minus sine theta over the little bit. So we use the addition formula to expand that sine theta plus h. And now we do some rearrangement slightly. That's just collecting terms. So cos theta has just got sine theta over h, whereas sine theta has got cos theta minus 1 over h. Let's do a little rearrangement to go cautiously and pernickety through this. So we'll leave that alone. But here we'll multiply the top and bottom of this by h over 2. And now we can see what's going on because, well, this term's easy. Sine h over h tends to 1 as h tends to 0. So this tends to cos theta. Cos h minus 1 over h squared tends to 1. So when multiplied by h over 2, it tends to 0. So this whole thing tends to 0. So that's the answer. So the derivative of sine is cos, but only if you work in radians, because this tending to 1 is only true if h is measured in radians. Okay, then the derivative of cosine, well, that's easy now, because we use the complement business. So cos theta is sine of pi minus theta over 2. Derivative of that is minus cos of theta, pi by 2 minus theta, and that's minus sine theta. So the derivative of sine is cos, and the derivative of cos is minus sine. Before moving on, it seems to me that it's a pity not to, in this little O notation, which is a friend of the Triddles notation, is not, I think, usually taught in schools. It really ought to be because it's a very pretty thing and very useful. It's a much better way of handling these approximations than is often done anyway. So let's see what it means. So what this means is that sine theta plus theta is, sine theta is theta plus something else, which tends to 0 even when divided by theta. So it tends to 0 faster than theta does. That's the parameter of the little o. So in other words, when you divide by theta, you get sine theta over theta equals 1 plus a term which tends to 0 as theta gets to 0. Actually, you can go further than this. I'm sure you know. You can get a more precise approximation so that the error term here is smaller than this theta third, and you get this for cos theta. Let's just look at this. Again, so this is that table we had before, sine theta over theta. And now you can see what this business is about, because so if theta is 10 to the minus 5, you divide this equation by theta. Theta squared over theta is 1 minus theta squared over 6, which is 10 to the minus 10 over 6, which is 0. Lots of zeros, 1, 6, 6, 6, 6, 6. On the other side, I'll just illustrate how good an approximation 1 minus theta squared over 2 is to cos theta. There's cos theta and there's 1 minus x squared over 2. So all this stuff that we've talked about so far was known to the Kerala mathematicians about 200 years before Isaac Newton and so on. They almost got to the point of doing differentiation, actually, but not quite. So now we're talking about waves, really, and I'm going to use t as the independent variable now rather than theta or x, because it usually is. It's usually time, and we're talking about something's varying with time usually. So if y is sine t, then its derivative y dot is cos t, and its double derivative y double dot is minus sine t, which is minus y. So it satisfies this equation. And in exactly the same way, if y is cos t, its derivative is minus sine t, and its double derivative is minus cos t. So they both satisfy that. But now if you look at that equation, and you think in terms of some application to the real world, there's really got to be a constant on this side, hasn't there, of dimension t to the minus 2, because whatever dimension y's got, it very often be length, this is t to the minus 2 times that. So there needs to be a constant here like that. So there is a constant which is usually written as omega of dimension time to the minus 1, for which that is true. Of course, it might be that omega is 1 in whatever units you're using, but usually it won't be. So that equation is satisfied by sine omega t and cos omega t. Crucially, omega is measured in radians per time unit, year or second or whatever it is you're talking about, and it's called angular frequency. Although notice we've left angles behind by now. There are no angles in sight in this. So pretty much from now on, in the subject of waves, trigonometry has left angles completely behind. Okay, so why is any of this relevant in the real world? Well, here's an example. Suppose you had a particle of mass m, and it's sort of sitting near some point of stable equilibrium, and it's sort of wobbling around it like this. And if it happens to be the case that the force pushing it back to the stable equilibrium point when it moves away from it is proportional to how far away from the equilibrium point it is, then we get this equation. So we have the return force of k times y, and then force equals mass times acceleration. So we get this equation. Well, so we know what omega is. It's root k over m. So knowing that return force constant and the mass tells you what k over m, and tells you that the solutions are likely to be cos omega t and sine omega t. So here are some examples. So this is Hooke's law. So the return force, if you stretch or compress a spring, is proportional to how far you stretched it or compressed it, and so you get what's called simple harmonic motion, which is this wave motion. Pendulum, that's approximately true. Well, a lot of this stuff is only approximate, really, and some of the interest comes later when we start trying to deal with the approximation. Here's a pretty example. This is a violin string. Again, the return force is proportional to how far the string is away from its equilibrium position. That's a much more complicated case, of course, and we'll get onto that later. And this is chemistry, which I don't pretend to understand, but again, we've got this wave motion, simple harmonic motion, roughly, because there's a return force which is approximately proportional to how far away you are from the equilibrium position. So it's a widespread phenomenon. So this is called the one-dimensional wave equation. The generals, we're not dealing with the general solution of differential equations in this video, but this is the general solution, it turns out. We learn at A-level how to turn that into this form if we choose. And so the general solution to this is a sinusoidal wave with an angular frequency that's determined by the equation, and then some amplitude and some what's called the phase. So they all look the same, really. They're all sort of translated and stretched versions of the sine graph. And this is how you turn from one form to the other. So, as I say, this is a very widespread phenomenon. And what's the history of it? Well, so Newton's revolution came when he established calculus and the laws of motion and the laws of gravity, and between them, those created this enormous explosion in the development of science and mathematics, which fed off each other, of course. So the big insight really was, well, that there are laws of motion, so the universe is a sort of machine in a sense, and that the laws of motion are the same in the heavens as they are on Earth. So up to this point, I think it would be fair to say that terrestrial science had made less progress than astronomical science. Once they were seen to be the same thing, they exploded. And trigonometry played a small part in that. The question is, what would have happened if Newton had never been born? Would it have made much difference? And the answer is probably not. We already know Leibniz created calculus at about the same time. The laws of motion, well, people were getting there, I think. So starting with Galileo, people were studying how things move on Earth, and I can't believe it would have taken very long for somebody else to have come up with those laws of motion. And actually, even the law of gravity, the inverse square law. So Robert Hooke had sort of guessed at that. How he'd done that actually without having either the laws of motion or the or calculus, I really don't know, but clever man. Anyway, he wasn't able to push it through, but surely somebody would have done so before very long. And then after that, well, Robert Hooke again, he of Hooke's law, was possibly the first person to write down the wave equation. Notice he's actually slightly older than Newton, but they were pals. They talked to one another. Brooke Taylor played a large part in this, another English mathematician. And sort of 2 generations later, this Frenchman was doing wave equations on a hugely more ambitious scale than anything we've looked at so far, illustrating this explosion in the development. So trigonometry had developed pretty slowly in the sort of 3,000 in the 2,000 years since between Aristarchus and Newton, and then it really quite exploded. So one of the things that one has to learn to do at school is solving equations like this. And this is really about waves, not geometry, of course, because that's why I've used a T here. Why would you want to solve an equation like that? Well, you've got some wave or other, and you want to know when it hits certain values. So a typical example would be tides. Actually, tides are rather poorly approximated by sine waves, but it illustrates the point. So you might want to know when is the tide going to be high enough that I can sail my ship up the river? Well, solving this sort of equation will tell you if you know the frequency, which you do because it's determined by the moon, and if you know this phase, which you can establish with one measurement of the tide, basically. So that would be a useful thing to know how to do. I find this an area that students come to me sometimes seriously confused. So I want to go through this a bit carefully and start by with a different equation. When we're solving quadratic equations, you do this sort of completing the square business, and you end up with an equation like this. So the key thing about this equation is that it's only got one occurrence of the unknown. And for equations like that, there's a systematic way of solving them. So you think about what would happen in reverse. Supposing you knew x and wanted to calculate this, what would you do? Well, you'd multiply by this, you'd add that, and you'd square it. So in order to get back from this to this, you have to undo those operations in the reverse order. So the first thing you have to do is find whatever it is that squares to this side. Well, you find one of those from the calculator nowadays, and the other one you just stick a minus sign in front. And then for each of those separately, you have to subtract that quantity and divide by that one, and that gives you 2 answers. And the completing the square business actually is the magic that turns a quadratic equation into an equation in which there is only one instance of the unknown. That's the key thing to this method. So now let's go back to this. Same principle, except that now we know there are going to be infinitely many solutions to this equation, not just 2. But it's the same idea. You find one of them. So the first thing you have to do is undo the sign, and you find one answer from the calculator. That's this one on this occasion. You find the other one by subtracting from pi using the supplementary principle. And then all the rest you find by adding some multiple of 2 pi. And then you do the same again. For every single one of those infinite many solutions, you first subtract this and then divide by that. And that gives you all your infinitely many solutions. If you think about the sort of function machine rule, what this is saying, if you started with any of those numbers and drove them through that function machine and then that one, you'd end up here. So I've got blue and black. There's no great significance here, but well, the black ones are the ones that correspond to the value you get out of the calculator, plus or minus some 2 pi's, and this is the supplementary one, plus or minus some 2 pi's. So how do you solve this? Well, this is what you do, is you take this and you back it through sine, you get all these infinitely many solutions, each of which you back through these function machines. But of course, you've actually seldom got the appetite for all infinitely many solutions. You're generally looking for solutions between some values. So, for example, if you're sailing a ship up the river, it's going to be, what hours of the day over the next week will I be able to sail my ship up the river? So you want a finite number. So how can you do that? Well, there are several ways to do it. You can just go back through this and generate a whole mass and go back through these things and see which ones end up in this range. It's a bit haphazard. You can, what you usually do, I think, is what, in fact, in practice, I usually do, is get these two out of the calculator and subtracting from pi, and drive those back through here, and then sort of guess how many more you need, and come back and generate another one or two of these and do it that way. There is, of course, a completely systematic way to do it, which is to start with the limits and drive those forward through the function machines to get these values, and then you just want to generate these, which is a bit easier, and then drive them all back through the function machine. That's actually, well, it's the most systematic way. It may not be the best, but in individual cases. Okay, anyway, so that's that. But this is all about waves, definitely, not geometry. There's another thing that's definitely about waves, which crops up in the A-level syllabus, which is this formula here. So if you take the addition formula in these two forms and add those together, and divide by 2, you get this formula. Well, that's very interesting. So it says, essentially, if you multiply two waves, you get the sum of two waves, or the average of two waves. That's quite remarkable. Again, this is really about waves. It's not about angles and things. I don't think you ever want to use this for angles, except in artificially created exam questions, perhaps. And there are other versions of this. Perhaps more interesting is to turn them around the other way and get these formula, which I had to learn at school. So this says the sum of two waves is equal to, well, twice the product of two waves. Isn't that interesting? Well, we'll come back to that when we study waves in a bit more detail, because these are interesting formulae in that context. But there's another thing these formulae can do, which has nothing to do with either geometry or waves. And that's the subject of the next video, the lost world of prostaphoresis. So what on earth is prostaphoresis? Well, that's the subject of the next video. Tune in to find out. Meanwhile, I hope you've enjoyed this video.